As humanity continues to push the boundaries of what we can achieve, one idea has emerged at the forefront of space exploration: producing rockets in space. But what challenges does this audacious idea present? Normally, as we all know, we construct our rockets here on Earth, a process that's time-consuming, expensive, and constrained by the planet's gravity. Building rockets in space could allow us to overcome these obstacles, but it's far from easy. Let's explore these challenges and hurdles. The first hurdle to overcome is securing the necessary materials to build rockets in space. Traditionally, all components of a rocket are manufactured on Earth using a wide variety of materials, including metals like aluminum and titanium, composites, and even rare materials for specific high-performance parts. Transporting these raw materials from Earth to space is one option. However, the cost of launching a payload into space is exceptionally high, and it gets exponentially costlier the more weight you add. For instance, as of the latest figures we could find, it costs around $2,000 to $3,000 per pound to send something to low Earth orbit using a SpaceX Falcon 9. Given the mass of a typical rocket, sending all the necessary materials from Earth would be exorbitantly expensive. An alternative to this is in situ resource utilization. This is the practice of extracting and processing materials from celestial bodies like the moon or asteroids. For instance, lunar regolith, the layer of loose, fragmented material that covers solid bedrock, has the potential to be used as a building material. Similarly, asteroids can contain a wealth of metals that can be mined and utilized. However, as of now, the technology to efficiently extract and process these materials is still in its early stages. It's also worth noting that both the moon and asteroids present their own logistical challenges. For the moon, you'd have to overcome its gravity when launching any finished materials. Asteroids, on the other hand, require significant time to reach. In addition, any materials gathered this way would need to be processed and manufactured into usable components. This would require advanced machinery capable of operating in the harsh conditions of space, which loops back into the second challenge: automation and robotics. Given the hostile environment of space and the complexities of manufacturing, human presence would be limited or perhaps even non-existent in the process of building rockets in space. Therefore, we would heavily rely on highly advanced and reliable automated systems and robotics. Autonomous systems would be essential for multiple stages of the rocket building process, starting with resource extraction if we're using materials from celestial bodies. These robots would need to be able to handle mining and processing raw materials, an operation which currently requires large, heavy machinery on Earth. Beyond resource extraction, automated systems would also be vital in the manufacturing and assembly stages. Here, precision is key. Every piece of a rocket has to be assembled with high accuracy, and the margin for error is minuscule. Think about the 3D printing technologies we have today. Then imagine them advanced to the point where they can print an entire rocket with absolute precision in a zero-gravity environment. Moreover, these systems would need to be self-sufficient, capable of troubleshooting and maintaining themselves. The delay in communication between Earth and space, coupled with the difficulty and cost of sending repair missions, makes real-time human intervention practically impossible. In addition, these robot systems need to be designed with the extreme conditions of space in mind. The space environment poses significant challenges in terms of temperature fluctuations, vacuum conditions, and radiation exposure. These conditions can have adverse effects on electronics, lubricants, mechanical systems, and materials, reducing their lifetime and reliability. The field of space robotics has been advancing rapidly with innovations such as the robotic arms used on the International Space Station and the rovers used for Mars exploration. However, the level of autonomy, reliability, and versatility required for in-space manufacturing is a significant leap from where we stand today. One of the most crucial aspects of rocket production, whether on Earth or in space, is ensuring the quality and integrity of every component. Rockets are complex machines where a single flaw can lead to mission failure, making strict quality control essential. On Earth, this process involves both human inspection and automated systems, all operating under precisely controlled conditions. Engineers can directly interact with the components, perform tests, and rectify defects. However, in the hostile environment of space, direct human interaction will be largely impractical due to cost, risk, and logistical difficulties. In a space manufacturing environment, the quality control process would need to be highly automated. Systems would have to be developed that can inspect and verify the integrity of each component during and after production, ensuring that every part meets the stringent specifications necessary for a rocket. These automated systems would need to be extraordinarily reliable and able to detect and rectify any defects or malfunctions on their own. But space presents unique challenges for quality control. The harsh environment in space, as mentioned previously, could affect materials and components in unforeseen ways, leading to potential quality issues that we do not typically encounter on Earth. For instance, some manufacturing processes that work perfectly in Earth's gravity and atmosphere may behave differently or fail entirely in a vacuum or zero-gravity environment. Furthermore, certain types of quality control inspections, such as those involving liquids or gases, could be significantly more challenging in the absence of gravity. Also, any materials sourced in space, such as metals from lunar or asteroid mining, may have different properties than their Earth counterparts, potentially affecting the final product's quality and performance. Developing automated systems and procedures that can ensure the quality of a rocket built in space in the face of these unique challenges would be a significant hurdle. Rockets are complex vehicles that undergo rigorous testing on Earth before they ever leave the ground. This is to ensure they function as expected under a range of conditions and to identify any issues that could jeopardize a mission. On Earth, a typical rocket testing regimen might include static fire tests, where the rocket's engines are ignited while the vehicle is secured to the ground; shake tests, where the rocket is subjected to the types of vibrations it might experience during launch; and various other tests to examine the strength of the structure, the functionality of the onboard systems, and the performance of the engines. However, testing a rocket built in space would present a host of new challenges. For one, some tests that are straightforward to perform in the Earth's atmosphere might be more difficult or impossible to carry out in the vacuum of space. For example, how would you perform a static fire test in an environment with no ground to secure the rocket to, or an environment where the rocket's exhaust has nothing to push against? Moreover, the microgravity environment might affect the performance of various systems and components in ways that aren't currently well understood. There would likely be a need to develop new testing methodologies and protocols tailored to these unique conditions. The delay in communications between Earth and wherever the rockets are being built and tested in space could also pose challenges. If an issue arises during a test, real-time intervention from engineers on Earth might not be possible. Lastly, in the case of a test failure leading to an explosion or other serious malfunction, the fallout could be far more serious in space than on Earth. Debris could become a hazard to other spacecraft, and the loss of an entire manufacturing facility could be catastrophic. Thus, coming up with safe and effective ways to test rockets built in space would be a substantial challenge to overcome in the pursuit of in-space rocket manufacturing. Any manufacturing process, especially one as complex as rocket production, carries the risk of creating waste or debris. On Earth, we have systems to manage and dispose of this waste. However, in space, the challenge is significantly more complex. Space debris, also known as space junk, is a term for defunct human-made objects in space. Old satellites, spent rocket stages, and fragments from disintegration, erosion, and collisions. These objects, especially those in popular orbits around Earth, pose a risk to both manned and unmanned spacecraft due to their high velocities. The manufacturing process for building rockets in space could create debris in several ways. For instance, small pieces of metal could be produced during the assembly process, or fragments could be scattered in the event of a testing failure or malfunction. Even small particles can become dangerous projectiles in the high-speed environment of space. Once debris is created, it's challenging to remove. It can stay in orbit for many years, and while efforts are being made to develop space debris removal technologies, no fully operational or proven systems exist yet. So, any space-based manufacturing operation would need to take great care to minimize the creation of debris and manage any waste that is produced. But preventing the creation of debris entirely might be impossible, given the nature of the manufacturing process. This means that techniques would need to be developed to capture or contain debris, or the manufacturing process itself would need to be designed in such a way that any debris produced is directed in a safe direction. The creation of space debris also has regulatory and legal implications. International space law requires countries to minimize the risk of creating space debris and holds them liable for any damage caused by debris from their spacecraft. Therefore, a space manufacturing operation would need to comply with these laws, adding another layer of complexity to the challenge. Addressing the space debris issue will require a combination of technological innovation, careful planning, and perhaps even new regulatory frameworks to ensure that our pursuit of in-space manufacturing doesn't lead to an unsustainable increase in space debris. Despite these challenges, the potential benefits of building rockets in space are immense. It could revolutionize our approach to space travel, making it more efficient and opening up new possibilities for exploration and colonization. Space is hard, but humanity's ingenuity and perseverance have always found a way to overcome the challenges it presents.